Let's start by looking at an example. We're asked to create a pattern that starts with a number and increases by 2. Then we're asked to find what algebraic expression describes the nth term of the pattern and to show our thinking. So let's look at an example. Supposing we want to have start with a number. Let's say we're starting with 3, and then we're going to add 2. So we're going to then go to 5, add 2 again, and we'll be at 7, and so on. So fairly straightforward. If we look at what the pattern looks like, here's an example of what the pattern looks like visually. Now we're asked to find the nth term of that expression or of that equation. So the next thing I'm going to do is I'm going to create a t-chart. And so I've got the term, which we'll call n, and then the value. And we've got 1, 2, 3 terms that are showing here. The first term is 3, the second term is 5, the third term is 7, and so on, all the way down until we get to the nth term, but we don't know what the value is at the nth term yet. So that's what we're trying to find out. So remember, each of these values, what we're trying to do is come up with an expression that shows how to calculate that value based on some value of n. Because what we ultimately want to be able to do is say, give me a value for n, give me any number for n, and I can tell you what the value is going to be. So here, if I give you the value 3, you can calculate the value as 7 without having to know what the previous numbers were. So here we got this number 7 because we knew that we were taking 5 and adding 2 to it. And we got the 5 by adding 2 to the 3. So that works if you're creating the whole sequence, but sometimes you want to just be able to jump and say, what is the 75th term that we're going to be? So I want to know what's 75. What's the value if n is 75? So that's where we want to get an expression that helps us get directly to the answer. In order to get there, we're going to end up doing something that is that creates an expression that's using the value of n. So in this case, I'm going to jump to the third one because sometimes it's a little bit easier to go further down in the sequence to see what's going on. We know we had 3 was our starting point, and then we've got 2 sets of 2 that have been added in. So we're going to add in 2 times 2. Remember, our order of operations says that we're going to do that multiplication first. So we'll have 2 times 2 is 4, plus 3 gives us 7, as expected. However, we want to have an expression that is based on 3 and not 2. So this is saying we've got 2 groups of 2, but we're working with the n value of 3. So what are we going to do in that circumstance? Well, let's look at this. So here, to get 7, we were using 2 groups of 2. In 5, we were only using 1 group of 2. So if you think about it, rather than being based on n, it's using the previous value of n. So here, we did 2 groups of 2 plus the original 3 to get us to 7. And to get to 5, we started with 1 group of 2, as you're seeing up here, and we're adding 3 to it. So rather than working with the value of n, we're actually working with the value of n minus 1 in order to get that value. So here, to get that 2, what we're really saying is we did 3 minus 1 times 2, and we added it to the 3. If we then take it more into the general case of n, we've then got 3 plus n minus 1 times 2. So in this case, if n is equal to 3, we're not going to be adding 3 groups of 2 into it, right? Because we've only got 2 groups of 2 that are added in. So you can see then that 3 plus 3 minus 1 times 2 is the same as saying 3 plus 2 times 2, which is what we started off with here. So we know that's giving us the correct answer. Now if we want it to be just back in terms of n, we have 3 plus. Now here we've got n minus 1 in brackets times 2. When we know the value of n, we do the work in the brackets first, but when we don't know the value of n, we can multiply it by the 2. If we're looking at how to multiply 2 times n minus 1, we take the 2 times the n, and then we subtract the 2 times the minus 1. So let's see how that works out. We end up with 2n minus 2. And if we now finish this off, we can collect the like terms. 3 minus 2 is 1, and then we just have 2n left over. So our final expression for this series is 1 plus 2n. So for any n value, we can now figure out what the value of the expression is going to be. So now for any value of n, we can figure out what the value of that term is going to be. So if we say that n is equal to 5, we know then that the value will be 2 times 5 plus 1, which is 11. Now let's look at another example. Supposing this time we started at 5, so we've got 1, 2, 3, 4 terms. That's our n value. And then the value of that term, supposing the first one we started with was 7. And we're going to do the same thing. We're increasing by 2 each time. So that means we go to 9, 11, and 13. Of course, we would go all the way down until we get to n. So the question then is, what is the expression for the value just using the generic term n? So if it helps us, let's go ahead and look at the layout of using tiles. In this case, you can see that we're using red tiles to show what's been added. So we've got the original group of 7, and each time we add 2, and then we add 2 more, and so on. We keep adding 2. So let's use the same approach as we used last time. We know that rather than relating to specifically n, we actually want to relate it back to n minus 1. So let's see what's happening here. We start off with 7, and then we add 2 to get 9, and then we add 2 to get 11, and then we add 2 to get 13. And we're going to keep adding 2. But if we've started with 7, as we did here, you can see that rather than adding, even though it's the second term, we're only adding one group of 2. And it's the same thing here. Even though it's the third term, we only have 2 groups of 2. And similarly, in the fourth term, we have 3 groups of 2. So the number of groups we have is again going to be 1 less than the term number. So n minus 1. N is the term number, and then we're going to multiply that by the amount that it's increasing each time, which is 2. So that's now the same as saying 7 plus 2 times n minus 2 times 1, which is 2. And we can subtract the 2 from the 7, and we get 5 plus 2n. Or you can say 2n plus 5. Sort of a more standard format. Usually we put the variable first and then the constant at the end. Now we're asked to create a pattern that starts with a number greater than 40 and decreases by 3. And they're asking what algebraic expression describes the nth term of that pattern, and to again show our thinking. So I'm going to create a t-table to help me out here, and I've decided that I'm going to start with a value of 45. So the first term is 45. The second term is going to decrease by 3, so that takes us down to 42. The third term, if I decrease 42 by 3, will take me to 39. The fourth term is 36, and so on, till I get down to n. So if I think of the value of, let's say we take the value of the third term again, I know I started with 45, so that's my initial value, and I'm subtracting some number. In this case, I'm always going to say n minus 1 times 3, and let's see if that works out. So 45 minus 3n plus 3, that's 48 minus 3n, or you could say minus 3n plus 48. Let's see if that works out when we put in the value of 3 for n. N equals 3. That means we've got negative 3 times 3 plus 48. Negative 3 times 3 is negative 9 plus 48. 48 minus 9 is going to be 39. So we can see that our approach of using the n minus 1 and multiplying it by 3 gives us the value that we need. So the algebraic expression for describing the nth term is 48 minus 3n, or negative 3n plus 48. The initial value of a pattern and the rate of increase or decrease are given. What is the rule for the nth term for each pattern? So the initial value is 2.5, and the rate of change is plus 3. So each time it's increasing by plus 3, and so on all the way down to n. So we want to know what is the rule, or what is the expression for the value of the nth term. Well, we know the rate of change is 3, and we know our initial value is 2.5. So I'm going to say that I start off with my initial value of 2.5, then I'm adding n minus 1 times the rate of change, which we can then simplify to 2.5 plus 3n minus 3. And when I collect the minus 3 and the 2.5 together, I get negative 0.5 plus 3n. Or I could say 3n minus 0.5. Let's check to make sure that is the correct value. If I put in n is 4, I get 3 times 4 minus 0.5, which is 12 minus 0.5, which shockingly turns out to be 11.5, which is exactly what we wanted it to be. Similar question now. This time we have an initial value of negative 3.5 and a rate change that is also negative. So our n value 1, 2, 3, 4. Those are always going to be numbers 1, 2, 3, 4, and so on, because they're just describing which term it is. It's always the first, the second, the third, and the fourth term. Our initial value is negative 3.5. The rate of change is negative 10, so if I'm subtracting 10 from that, negative 13.5, then negative 23.5, negative 33.5, and so on all the way down to n, and we want to know what's the expression for the nth value. So we start with our initial value of negative 3.5, then we're going to add to it whatever the rate of change is, which in this case is n minus 1 times negative 10. So that's negative 3.5 plus, I'm going to leave in some brackets here, negative 10 times n is negative 10n, and negative 10 times negative 1 is positive 10. So now after to resolve this, I want to get rid of the brackets, so that's negative 3.5 minus 10n plus 10. Now I collect the 10 and the negative 3.5 together, and I get 6.5 minus 10n is the expression for the nth term. And let's go ahead and just double check that with the value of 4. If n is equal to 4, then that means our value will be 6.5 minus 10 times 4, which is 6.5 minus 40, which is negative 33.5, which is exactly what we were hoping to find. Lesson summary. A linear pattern increases or decreases by the same amount from one term to the next. That's also what we refer to as an arithmetic pattern. For example, 4.5, 7.5, 10.5, 13.5, 16.5, they all increase by 3 each time. 40.8, 33.8, 26.8, 19.8, and so on all decrease by 7 each time. A pattern rule lets you describe any term in a pattern. The rule is often written algebraically using the variable n. The nth term of a pattern refers to any term in that pattern. For example, each term in the pattern 2, 4, 6, 8, 10, 12 is the term position multiplied by 2. The 5th term is 2 times 5. The 10th term is 2 times 10. And the 58th term would be 2 times 58. You can say that the nth term is 2 times n, or 2n, which means you multiply the value of n by 2. You can show patterns visually. These square tiles show the pattern 2.4, 4.4, 6.4, and so on. And you can see that there's a 0.4 included there. And as you progress to each subsequent term, you're just adding in an additional 2. And if you think about it, that makes sense. The difference between 2.4 and 4.4 is 2. The difference between 6.4 and 8.4 is also 2, and so on. It's always a gap of 2. So here you're just adding in 2 for each subsequent term. The 5th term is the total of tiles in the first 5 rows. The 10th term is the total number of tiles in the first 10 rows. The nth term is the total of number of tiles in the first n rows. The tiles show that when there are 5 rows, there are 5 sets of 2, plus the extra 0.4 tile in the first row. So 5 times 2 plus 0.4 is equal to 10.4. When there are 10 rows, there are 10 sets of 2 plus the extra 0.4 tile in the first row. So 10 times 2 plus 0.4 is equal to 20.4. This means that when there are n rows, or some unknown value n, there are n sets of 2 plus the extra 0.4 tile in the first row. So there you end up with 2 times n plus 0.4. Note that adding a new row is adding 2 because the pattern goes up by 2. You could also show this pattern with square tiles this way. Each term is 2 more than the previous term. So you see that here. There's the 2 added in, then another 2 on the next term, then another 2 on the next term. The dark tiles show the constant, which in this case is 3. That's part of each term. The light tiles show the 2 tiles added each time. So the 5th term is 2.4 plus 4 sets of 2, or 2.4 plus 8. The 10th term is 2.4 plus 9 sets of 2, or 2.4 plus 18. The nth term then is 2 plus n minus 1 sets of 2, which is equal to 2.4 plus 2 times n minus 1. But 2.4 plus 2 times n minus 1 is equal to 2.4 plus 2n minus 2, which is equal to 2n plus 0.4, which is the same rule as the rule we used to describe the pattern above originally. You can relate a linear pattern to another simpler pattern as long as both patterns grow by the same amount. For example, you can relate 4.8, 7.8, 10.8, and so on to 3, 6, 9, and 12, and 15 because the interval between each one of them here was always increasing by 3, which is the same interval as we have here. To get to any number in the second pattern, you just multiply the position by 3. The 10th term is 10 times 3, which is equal to 30, and the 20th term is 20 times 3, which is equal to 60, and so on. This means the nth term is 3 times n. Every term in the first pattern is 1.8 more than the same term in the second pattern. So the nth term is 3n plus 1.8, and the 5th term is 3 times 5 plus 1.8, or 16.8. Key terms. Coefficient. The coefficient is a constant value placed before a variable that multiplies that variable. For example, the 5 in 5x, or the 9 in 9y, or the 2 in 2m. In each case, the 5, the 9, and the 2 are coefficients. The general term, or nth term, is an algebraic expression that describes any term in a pattern. For example, the general term 5n plus 1, where n represents the term position, describes any term in the pattern 6, 11, 16, 21, 26. Linear pattern. A linear pattern is a pattern in which the value of each term is greater or less than the value of the term before it by a constant amount. For example, 2, 4, 6, 8, or 15, 12, 9, 6, 3 are linear patterns because the gap between each term is constant. The pattern rule is a description that tells how a pattern starts and how it continues. For example, a pattern rule for 4, 7, 10, and 13 is start at 4 and add 3 each time, or 3n plus 1. So the pattern rule is really kind of a word description of what's going on, or in some cases we're allowing to use just the general term. Finally, the term or pattern is each number or shape in a pattern. So when we've got a t-table, where we've got n and the value, these are the term number, and the numbers we end up in the value column, these are the terms.